Hello everyone, and welcome to this new section in which we are going to be building our own variational autoencoder models from scratch. Previously, we saw how variational autoencoders could be used in helping to generate new images, where we build out this encoder-decoder structure such that we could produce outputs which are similar to the inputs while being entirely new images. In this section, what we'll be doing will be to build our own variational autoencoders and generate our own images. The data we'll be using in training our variational autoencoder will be the MNIST dataset, which you could get from Tensorflow datasets. So right here, we load this dataset and then we concatenate both the training and the test datasets. So generally, we usually have a dataset made of say X train and Y train, X test, Y test. But since here we are not going to be making use of this outputs, that's the Y train and Y test, we just get this two and then we concatenate both, since we will not be having a test set. So basically we have that, and then one other modification we make is one other preprocessing step we take is we divide these values by 255. So we normalize our data set. So let's run this, and then once our data set has been downloaded, what we do now is we convert this data set into the TensorFlow data format. So we have our data set, which is TF data set, or rather data, TF data set from tensor slices. So you see that we take that and then we pass in our MNIST digits, which we've already downloaded. So we run that and that should be fine. Now we could check out the length of this data set, and you see you should have 70,000. So we have 70,000 different data points which make up our data set. From here, we're going to define the batch size. So we would have a batch size of 128. That's it. And then we'll go to the usual steps of shuffling our data set. We have our data set, we shuffle, we batch, and then we prefetch. Now, if you're new to this, you could check out the previous sections in this course. Anyways, we have this 3 as we've said, and then now we could run this. So that's it. Could say train data set. There we go. You see that we have this train data set here, and we could see its shape. So it's all 28 by 28 by 1 images we have in our data set, and there's 70,000 of them. So that's fine. Now, getting to the modeling, we're going to start with the encoder. You can recall that what we had seen so far was this model, or this encoder model, which takes in an input image right here and then outputs the mean and the variance. So we have the mean and the variance, and then these two have been combined via the reparameterization technique, where we have mu plus sigma times a random value drawn from a normal distribution, and then this z is passed into a decoder here. So we pass z into a decoder, and then we get an output image such that the difference between these two is minimized. Now that said, let's get back to the code and we design our encoder. So our encoder here is going to be a very simple convnet. We'll start by defining the latent dimension. There we go. Let's just put this right here. So latent dimension will be 2. We have that, and then we get back here. For our encoder, we're going to start, as we said, with this encoder input. So we have an encoder input, and then this has a shape which we're going to give to be 28 by 28 by 1, just the same as that of our images in our data set. So that's the input. We've seen this already. And then from here, we'll define a conv2d, which has 32 filters, 3x3 activation ReLU. So we're supposing that you already have some background knowledge on convnets. Activation ReLU, number of strides equal to the padding same. So we're going to build this very basic convnet. Now this takes in the encoder inputs. Remember or recall we're using the Keras functional API right here. So we have encoder inputs. We then create another conv layer. We just basically copy this and paste it out. And then what we would have here is an increased number of channels. So we have 64 here. And from here, we'll go ahead and flatten our outputs. Now note that here we have X. So we should change this to X. From here, we move on to flatten. So we have flatten, and this takes in X. So now the output is flattened. We are now going to output both the mean and the standard deviation, which we are going to use in sampling. But before that, we'll pass this into another dense layer. So here we have this dense layer, could say 16 outputs, activation ReLU, and then we take in X. Okay, so we have that, and now we're ready to, let's just copy from here. We're ready to get the mean and the standard deviation. Copy that, paste it out here, and this. Okay, so here we have the mean, and we'll have the standard deviation. So we have dense, activation ReLU, standard deviation, and then here, since remember we have this output to be the latent dimension. So here we have, instead of 16, we now have latent dimension, which we've already fixed right here to be 2. Now, one very important reason why we have those activations to be ReLU here would be simply the fact that the mean and the standard deviation are all positive numbers. So because we may output or we may get negative numbers here, we want to always make sure that the values we get are positive. Now, the problem with the standard deviation particularly is the fact that it's usually a very small number between 0 and 1, where the number is very far away from 1, meaning that the number is instead closer to 0. So we'll have a number very close to 0 like this. But then the problem with working with the ReLU is that having to find derivatives around this 0 here will lead to numerical instability during training. And so what we want to do instead is to map this range of values, or this possible range of values that the standard deviation can take, to a larger range. Now, to carry out this mapping, we have to use a function which is both continuous in this range and monotonous, that is either increasing or decreasing. Now, one great function for this task will be the log function, as this log function will map values of x in the range 0 to 1 to values in the range, let's open it up here, in the range negative infinity. Log, the limit as we go to a 0 of the log is negative infinity. If you plot out a log, you would have something like this. Let's have something like this. So you find that as you go towards 0, log goes towards negative infinity. So that's why we have negative infinity here, and the log of 1 is 0. So we go from this range to this larger range. Hence, we can have a much more stable training process. And so what we'll do now is, instead of relying on this ReLU activation to ensure that our standard deviation is always positive, what we'll do is we'll instead compute the log of the standard deviation square, which happens to be the log of the variance. So we're going to take this off for both the standard deviation and the mean. Let's take that off. And then right here, we have log var. That's a log of the standard deviation square, log var. And then we'll move on to the sampling process where we're going to obtain z. Remember, z is equal mu, which is the mean, plus the standard deviation times epsilon, where epsilon here is a random number drawn from a normal distribution. We are now going to create the sampling layer, which takes in the mean and the log of the variance and then outputs the z. So here we have z equals sampling. There we go. We're now taking as inputs the mean and the log of the variance. And that's it. So from now we're going to create the sampling layer. So let's go ahead and create the sampling layer. So we have here sampling. There we go. And this is a layer. Okay, so we have that. Then we just have this call method, which takes in our inputs. Let's just have our inputs. And then from those inputs, what we would have is the mean and the variance. So basically we have, or we extract the mean and the variance from those inputs. Remember, we have the mean and a log var. Let's say mean and the log var actually. So we have that mean and log var, which we extract from the inputs. And then if you remember what we have here, so the way we obtain z is mu plus sigma times this random number right here. Now let's see how, when given mu, when we get mu and we get the log of the variance, we are able to obtain this sigma, because we already have mu, but now we need to get sigma. Now note that sigma is a standard deviation, and the standard deviation, or let's just write sigma, and sigma itself is equal the square root of the variance. You see that? It's equal to the square root of the variance. So it means that and then we know that the variance written like this can be written as e, that's exponential, to the power of log of the variance. So generally we know that x equal e to the log of x. You see that? So here we have e to the log of the variance, and then we also have the square root. So let's have this here. Now this is equal e to the log of the variance. Let's just leave that at v, and all of this to the power of a half. We also know that e to the power of say x to the power of all of this to the power of a is equal e to the power of ax. See that? So here this is going to be equal e to the power of half times log v. So it's going to be half log variance. So now that we have the log of the variance, to obtain the sigma, this is basically what we need to do. So let's get back, and then we have the mean plus sigma, which is exponential, and then we have half, so 0.5 times the log of the variance. And then we need to multiply this here, the sigma, by random value. So we have TF, the random normal, and then we specify a shape, which is simply the batch size, and latent dimension. Now that we have this, we can now go ahead and define our encoder model. Call this encoder model, which is a Tensorflow model, and we have encoder inputs for the input. There we go, that's it here. And then for the outputs, we have this list made of z, the mean, and the log variance. So we have mean and log var. Okay, so let's give it a name. We'll call this encoder. Now, once we have this, we could get a summary of this. So we have Encoder Model summary, which we could visualize right here. See that? From here now, we will move on to defining our decoder. The decoder, as we've seen already, will take in the Z here and then output the images. So we'll go ahead here and create the inputs, call this latent inputs. And then there we have TensorFlow input, and shape is gonna be the same as that of Z. So right here we have latent dim, and that's fine. Okay, so now we have this. We're gonna take our Z. Let's get back here. So now we have to upsample this Z here, which has a shape, to now an image of shape 28 by 28 by 1. But generally, what we've been doing is we've been used to downsampling. So in downsampling, we have an input, we have some ConvNet layers, we stack them up, and then when we get towards the end, we could flatten, and then we have some dense layers with a specific output which matches the type of output we want to get. But in our case, we're now doing some sort of the opposite of this. So what we'll do is we'll go through some dense layer here, we'll go through some dense layer, and then from this dense layer, we would pass this into a transpose convolution layer. So we've been used to the convolution layer, but here we instead use the conv 2D transpose layer. Essentially, what we have is this conv 2D layer with its weights, which upsamples inputs. Now, getting back to the code, we have this input which has shaped batch size by the latent dimension, let's say 2. And then from here, we want to make use of a conv 2D transpose layer which takes inputs batch size by some X, by some Y, by some Z. That's similar to the conv layer. So what we will have to do is we're gonna reshape this actually. So we have to reshape this such that we have something like this. Now, if we want to have X, Y, Z such that X is, say, for example, 7, Y is 7, and Z is, say, 64. Let's take that example. Then we have to ensure that what we get in after this has shape B by this 7 by 7 by 64. 7 times 7 times 64. You see? Getting back here, we have this. Let's maybe redraw this again so it's clear. So what we're saying is we have this input, and then what we intend to have is something like batch size by 7 by 7 by 64. Now the reason why we're picking 7 is because the output is 28 by 28. So we want to be able to upsample such that we could say 7 by 7 upsampled to 14 by 14, and then the 14 by 14 upsampled to 28 by 28. So that's why we're picking 7 here. Now this year, you see, it doesn't match with this. There's no way we could reshape 2 to become this. So what we'll do is that we'll pass this through a dense layer which has outputs batch by 7 times 7 times 64. And now after reshaping, we could obtain this. So let's get into the code, and what we'll have is dense layer, we have dense layer 7 times 7 times 64, and then we have the activation relu, and this simply takes in the latent inputs. So we have here latent inputs. There we go. Then from here now we do the reshaping. So we have x equal reshape, and then we specify the shape. So we have 7 by 7 by 64. So that's it. Now we have that, we have X, there we go. We now start with our conv2d transpose. So you see we'll reshape this into this now. I could make use of our conv2d transpose. Conv2d transpose, which takes in number of filters, is very similar to the conv layer. So we have a number of filters, let's say 64 filters, and then the kernel size 3, the activation relu. So we're going to use the relu activation, number of strides 2. The padding is going to be the same. See, so it's quite similar to the conv layer, but with the difference that now we upsampling instead of downsampling. So we have that. Then from here we are going to change this to 32. So for the encoder, what we did was we increased this number of channels, and then here we reduce the number of channels. Now in our final output layer, we're going to have this decoder output, which is going to have just one channel. So here we have an output which is 28 by 28 by 1, where the values lie between 0 and 1. So what we're going to do now is we're going to have channel numbers equal 1. The activation instead of relu will be sigmoid. So here we have sigmoid, and then we're not going to use any strides since we're not upsampling. So that's it. Now the reason why we're using sigmoid here is quite simple. Since we want our values to fall between 0 and 1, we want that each and every time we have an input, we have something like this. So no matter the input we have, the sigmoid will always put the value, or make that input turn into a value which lies between 0 and 1. And that's basically what we want to do in this last layer right here. So that's why you see we're making use of the sigmoid. Now once that's done, we create our decoder model, which is Tensorflow model, and then we have latent inputs. There we go. We have our decoder output. The name is decoder, and then we could get a summary of this model. So that's basically it. Let's run that. And there we go. See, we have our decoder model. Now for the training, we are going to make use of the Adam optimizer with a learning rate of 0.001, and we're going to train for over 20 epochs. Now, as we've seen already, our loss will be made of two parts. That's the reconstruction and the regularization part. Now for the reconstruction part, our aim is to minimize the difference between the outputted image and the input image. So we'll go ahead and start with the reconstruction loss. We have our custom loss. There we go. It takes in y pred, takes in y. Let's start with y true. Takes in y true, y pred, and then the reconstruction loss itself is defined such that we have let's just say loss reconstruction is equal tf keras losses binary cross entropy loss. Okay, so our outputs, remember our outputs range between 0 and 1, so we could use the binary cross entropy loss here. Feel free to test other different losses. So we have that, and then we pass in y true and y pred. Now once we make use of this, we are going to now sum all the values, because we have let's say we have something like this. Let's suppose that it was 5 by 5 outputs we were having. So we would have something like this, 1 2 3 4 5. That's fine. 5. There we go. You see, we have this 5 by 5 here. So with this binary cross entropy, we'll be able to get the difference for each and every position here. Now we need to sum all this here. So what we would have is, let's take this off. We'll take this off, and we'll have the reduce sum. So this reduce sum now will sum all this different these different loss values we get here. So now we sum for each and every position. Obviously we have 28, so it's 28 by 28 positions. We also need to specify the axis here. So the axis we're going to work with is 1 and 2. 1 and 2. Now to understand why we're having this, let's take a look at the shape of the output. It's b by 28 by 28 by 1. But where we're actually carrying out this, or where we're actually computing the loss, is in this axis here. So we specify 1, 2 because this is 0, 1, 2, 3. So this is where we want to compute our loss. So it's on these two axes. Now said we have that, and then we now look for the mean. So we could, after summing up, we could look for the mean. Let's average the values, and that should be it. So that's it for our loss reconstruction. The next step, let's take all this off. The next step will be this loss regularization. Getting back here, you see we have this sum. See the sum of the variance plus the square of the mean minus 1 minus the log of the variance. So let's get back here, and we have this -1/2 here. If you take this negative and multiply by each and every one of this, we would have log var plus 1 minus the mean square minus the var. Before we continue, remember again that we could get sigma j as e to the log of sigma j. See that? So no, let's rewrite this better. So we have sigma j equal e to the log of sigma j. Okay, so that's it. Let's get back here. We have loss. We'll still have this mean and sum. So we'll sit average sum and then find the average. Let's have that, and then we'll have -0.5 times the log var. Let's get here. We'll need the log var. Let's say log mean, and then let's get exactly what we had here. Remember, in this encoder model, we outputted the mean and the log var. So let's have mean. There we go. We have mean and log var. Okay, so we have this set. Now we could make use of it right here. We have, as we've said already, log var plus 1. So we just have plus 1 minus the mean square. So tfmat mean, rather the square of the mean, and then minus tfmat e to the power of log var. See that? And now we return the loss reconstruction and the loss regularization. So that's it. So this is our custom loss. We run this. We get in this error. Let's add this and run that again. Okay, so that's fine, and we're now set to start with the training. But before going on, we have to also specify the axis for the sum. So right here we have this axis, which is equal 1, and we explain why we specify this axis to be 1. Now the shape of the log var and the mean is this batch by 2, and so the shape of all the sum will still be this. And so if you're comparing this, or rather if you're computing this here, you'll get this kind of output. And so since for the loss we need a single value, we need to sum all the values we get in this axis. So that's why you see we specify the axis to be 1. We have this input which we define. Then we have the encoder model which outputs z, the mean and the variance, which we're not going to make use of. And then we have the decoder which takes in z and then produces this output. So here we have this VAE model which contains both the encoder and the decoder. Now we're going to go ahead and build our custom training block. We suppose that you already have an idea of how this works. So we have that training block which takes in our X batch. And then we're going to make use of TensorFlow's gradient tape. So we will have this with TF gradient tape, there we go. As a recorder, we're going to pass this batch into the encoder. So we have our encoder model which takes in X batch, and then what it outputs is Z, the mean, and the log variance. Here we have this. Okay, so we have that set, and then now once we get this, we get the Z from here and pass this into our decoder. So we have our decoder model which takes in Z, and then what it outputs is our Y predicted. See that? And now from here we could obtain our loss by simply calling on our custom loss method which we've defined. It takes in the Y true, it takes in the Y pred, it takes in as we've defined here the mean, and it takes in the log variance. Now this Y true happens to be the X batch. Remember, we're having this here, this encoder takes in that. So we have our input image here. Let's take this off and draw it a bit here a bit clearer. So here we have this and we have this. So we have our encoder and we have our decoder. We have our input image, which is what we expect to have here. So our Y true is what we pass as input here, which is this X batch. So that's why you see we specify Y true as X batch. Then Y pred is what the decoder produces. So we're going to compare the Y pred and then the Y true, which is, as we've said already, the X batch. That's fine. We get back to the code. We have that set, and then now we have our partial derivatives, which we will get by making use of the recorder. So we have recorder gradient, it takes in the loss, it takes in the overall model's trainable weights. So we have trainable weights. Okay, so talking about the overall model, which we yet to define, we have it right here. It takes in this input 28 by 28 by 1. It takes the input, pass into the encoder model, gets the output from the encoder model, and then into the decoder model, and then from there we create our model which takes in VAE input and this output right here. So from here, let's get the summary, and we see that we have exactly what we expect. So we have this model which takes, as we've said already, this input, the encoder outputs Z, the mean and log var, and then the decoder outputs this image right here. So let's get back to our training. As we're saying, where we have this partial derivatives from the loss and the trainable weights. So that's it. We then go ahead with the gradient descent step. We apply the optimizer. So we have optimizer.apply gradients, there we go, which takes in our partial derivatives and our trainable weights. So there we go, we have the Z partial derivatives, which we just calculated right here, derivatives, and then the trainable weights, there we go. Okay, so that's it. We could from here just simply return the loss. Now we're gonna run this, and we haven't run this yet. Okay, so we have that already. Now we could define our neural learn method. So we have here neural learn, which will take in the number of epochs, and then from here, for the epoch in range epochs, there we go, we're gonna start by printing out the training starts for epoch number, whatever epoch we are at. So we format that to take in the epoch +1, since we're going to start from 0. Or we could just take this 1 from here, and then there we go. Now we have to add +1 here. Okay, so we have that, and then now we're gonna do for step X batch, we're gonna enumerate. In enumerate the train data set, which we've defined already. Let's get back to the top, and we see we have our train data set. So we're gonna go through this train data set. Let's get back here. There we go. So we go through our train data set. We take a specific batch, and then we compute the loss. So we have that training block, which we've defined here. Our training block has been defined here. So not only we compute the loss, but we also apply the gradient descent step for that specific batch. So we're doing this for each and every batch of our training data set. Now what this takes in is our X batch. Simple as that. Now once we have this, the next thing we'll do is we'll print out our loss. So the training loss is there we go, we have loss. And then once the training is complete, we could simply print out training complete. Okay, so we have that set. Now let's run this, and then we have neural learn. Let's train for epochs. Here we get in this error. Let's take that off. That's fine. Let's run this again. So training is now complete, and here's what we get. You see that our loss drops, and then we can now get straight into testing out our VAE model. Now before testing, let's recall that our VAE is comprised of 2 units. That's our encoder and then the decoder right here. Now we've trained this VAE model end to end to make sure that the inputs look very similar to this outputs produced. Now if we want to generate new outputs, what we'll do is we are going to cut off, or we are going to take off this region here and focus only on the decoder. Now to generate an image at random, or to generate a digit in our case at random, we'll just have to pass in a z in here. That's a random value of z. Remember, z is mu plus sigma epsilon. So we have to pass this value of z in here and then get a random output. Now remember, z is 2-dimensional. So z is this vector made of 2 values. And so that said, we will define the first values here, which we'll call grid x, and we use the linspace method to get values from a scale. Let's add a cell above this. So we would have a scale which will take a value of 1, and then we will have n equals to say 16 different values. So here we go from -1 to 1, and then we'll have 16 values in between. We'll repeat this for grid y. Now, so this is the first element, and this is the next element. So here we would have different elements so that we could generate different images. There we go. Let's run this and then print out grid x and grid y. Now that we have this done, the next thing we'll do is we'll plot out our different images, which we shall generate using our decoder. So here we have this figure. We'll define the fixed size. Let's say 5. Anyway, 5 by 5. And then for I in grid X and for J in grid Y, we define the different subplots. Subplot 5 by 5 by k plus 1. Let's define k right here. So k equals 0. Okay, so that's it. This is grid, not grad. We have grid that way, and then now we're ready to use this grid x values, that's the values of I and j, to generate new images. Okay, so what we'll do now is, this is plt, the subplot. So what we'll do now is we'll have our input, which is TensorFlow constant, and then we have ij, so these two values, and then from here we have the output, which is our VAE, but notice how we pick out layers 2. So to better understand this, you should get back here where we defined our VAE model. So here you see this is the VAE, our variational autoencoder, which is made of different layers. So this is layer 0, layer 1, and then layer 2. If you do VAE dot layers, let's say 0, see you have this input layer right here. Now if you change this and say, anyway, let's say for I in range 3, there we go, we're gonna print this out. So we're gonna print our layers I. Let's run that, and we see that we have this input layer, we have this functional model, this other functional model, but you should note that's basically our encoder and our decoder. Okay, so that said, we're gonna make use of our VAE layers here. So we have VAE layers 2. This is to say that we're using the decoder actually. So our decoder is gonna take in the input. See that? It takes in the input. There we go. And then we'll have to select our first axis here. So that's why we have this. And then we have to select this other axis right here. So such that our output now, you see, if we do this, if we have 0 here, we do this. See, this is not going to be transformed to 28 by 28. So basically that's why we do this. Now once we have that, we do the im show, and then we have our output. Our map is gray. There we go. Plot axis of, and then k plus equal 1. Okay, so we basically increasing the value of k, sorry, so that we could have this as different subplots. So let's run this now and then see what we get. We get in this error here. So this is actually because we are having many more values as compared to what we defining here in this subplots. So what we should have here should be n, and here should be n. That's set. Let's run this again and see what we get. Now as you could see, we are able to generate these digits making use of just this z vector right here, which is composed of 2 numbers. Now one thing you can notice here in this latent space is that as we go from values of -1 to 1 in this 2-dimensional latent space, the outputs are created or generated such that in each line, as you could see, we have one digit which is being slowly morphed into another. You see here, we start with a 9, but as we change values in this latent space, you see slowly we get to 8, and then here you see 8, and at this point you start with a 9, and then you slowly get into 5s, and so on and so forth. You can look at this horizontally as well as vertically. See that? You could get to 6 and that, and then you could also look at this diagonally. See 9, 8, 3, 2, 6, and then you get to zeros. So for this first line or this first lines, you could look at this first lines as going from 9 to 8. Then here it's like from 9 to 5, but passing through 3, see, and so on and so forth. So basically, this is how we generate images using variational autoencoders. At this point, one question you may ask yourself is, we are having this outputs which are being generated from the making use of this z vector right here. But how does the z vector, this z vector here of the different images vary with the particular digits in those images? So how does a z vector in, say, let's take this for example, in 6 vary with that of 0, with 2, and all other digits? To experiment with this, we'll copy out this code we had already and then get back here and now try to pass in the different digits into our encoder and then plot out the positions of our z vectors and then see whether there is some correlation with the z vector position and the input we have here, right here, or the specific input digit. That said, we're gonna make use of this, so we have that, and then here we're gonna have our Y train. So this time around we'll be needing the Y train because we need to know exactly what digit we're dealing with, unlike here where we just needed to have the input images. Okay, so that's it. We have X train, Y train. We're gonna reload this and then we do the usual pre-processing. From here we run the cell and then we move straight away to pass in these images in our encoder. Now similar to what we had here, now we're going to be making use of our VAE layers and then picking out the first index. So here we have output. We could call this, basically we have Z, then we have the mean and the variance, and then this is equal, let's copy this here, there we go, we have that, then this is now 1, see that, and then from here we pass in this X train. So that's it, we pass in the X train and then we could go ahead to start with the plotting. Plot figure, specify the figure size equals 12 by 12. There we go. And then we do a scatter plot. Now the scatter plot will show us the different positions of the values of Z. That's the Z points in our two-dimensional space. Let's take this off. There's different Z points. And then also we're going to color this such that digits belonging to the same label have the same color. There we go. We're going to plot this as our X and then our Y. So we have that, and then now we specify this Y train as our labels. So that's it, and then we can now go ahead to plot out this color bar and show. Let's run that, and here's what we get. As you could see, the labels here go from 0 right up to 9, and then you could notice these different clusters we have in here. See these different clusters? See that? This shows that the encoder part of our variational autoencoder has been trained such that now it's able to generate values of Z where this point is outputted such that two inputs belonging to the same digit will be closer to each other as compared to two inputs belonging to two different digits. So what we've been doing so far is we've been training the variational autoencoder model with our own custom training block. You see right here, we made use of this gradient tape and we carry out the gradient descent manually, as compared to when you just have, say, a model fit and then you pass in your train data set, and basically this takes care of doing the training. Now, the advantage of working with this fit method is that it's quite simple to use, but compared to this custom training loops, it doesn't give you that much freedom, and that's why we're making use of this gradient tape here to train our model. Now, with TensorFlow, it's possible to actually get the best of both worlds. Now, this means that we can be able to train or get this custom training right here and then still make use of the fit method. The way this is done is by overriding the train step method of our model, which we shall define. So that's said, let's get right here and define this VAE model. Then we go ahead and define this model as we would do with a usual Keras model. But just as we had done right here, that's in this VAE model we had built here, we need to take into consideration, or take as argument here, the encoder model and the decoder model. So that's it. Now, once we have these two models, we have here our encoder, which is our encoder model, and we'll do the same for the decoder. Now, once we're done with this decoder, let's type this out. We have your decoder. As we're saying, once we're done with this decoder, the next thing we want to do is define some loss. So here we have our loss. It's actually a loss tracker. Now we'll get to understand better why we call this a loss tracker. So here we have the average or the mean of the different losses which we shall get. And then from here, we'll go ahead to this main section where we shall override the train step method. So just like, let's add this here, just like we used to working with methods like model, like the compile method, like the fit method, here we have this train step method, which is called each time we call on this fit method right here. But since we are not going to make use of the default fit or the default train step method, we would have to override this and write out our own training block, which is basically this block we have here. So what we could do here is copy this out. So we could simply copy this out and then paste it out here. Now let's just copy all this. There we go. And that's it. We paste this out. So here we have our training block. We'll call this train step. So we override this train step method, which is a Keras model method. So here we have our train step. We're taking in our batch. There we go. And then it's going to be similar to what we've had already in the training block. So you see here, we have our z mean log var, which is gotten from the encoder model. And from here, we pass z and then we obtain y pred. We have our y true. We obtain our loss. We've already defined our custom loss method, and that's it. Then from here, we're going to update our loss metric. So here we have loss tracker, which we defined already here. We're going to update its state. So we update our loss state with the value of this loss. So that's it. Now we are going to return the result. So we have this dictionary, we have loss, and then we have our loss tracker dot result. See that? We have that. So there we go. We have updated our loss. We output a loss. But one important method we need to call again is the metrics method. So here we have metrics. You could define several metrics, but here we just have this loss, and then we return our loss tracker. So we have loss tracker returned. Now notice how this is actually a list. So you see this is a list because we could have say different losses which we could return, and then we have the property decorator which we place right here. So once we have this set, you see, we do not need anymore to make use of this or to write this as it was written. And so this means that we are not going to be writing out, for example, training start for epoch this, the training losses this, and all of that. Now all we need to do is just call on our model.fit method. So right here, let's run this first. Let's run this right here. There we go. And then we go ahead. We're getting an error. Now from here we define our VAE. So it's quite similar to what we had already seen here. See that? Now we have this VAE, which is now this VAE which we've created here. So let's have that VAE equal VAE, and then it takes in the encoder model and the decoder model. That's it. So once we have this, now we could do just as we used to doing. Let's even say model. Let's just say model, and then here we have model.compile as usual, and then here we're gonna pass in our optimizer. So here we have optimizer. I guess we had defined this optimizer already. So let's check here. Yeah, we had defined this optimizer. So here we just have optimizer equal optimizer, which we've defined already, and then we do model.fit. See that? So that's all. You just need to now make or call this fit method, and then we have our train data set, which we pass in the number of epochs. We'll define this to be 20, and then the batch size equal, say, 128. So that's it. So here, unlike before where we needed, for example, to specify the optimizer in this way and then actually get in depth to understand that this gradient descent process needs, for example, the partial derivatives and the trainable weights. Now you'll see that unlike before, where if you were, for example, needing to make use of some callbacks, you would have to write that or include that in here with some custom code. But now all you need to do is just have callbacks. So we both able now to write our own custom training loops while still taking advantage of everything that comes with the fit method. So right here you could have some callbacks, and that'll be it. Anyway, let's take this off, and then let's get back here where there's this slight error. You see here we have this VAE.trainable weights and that. Now this was in the case where we had defined our VAE this way. We had this model and then get into our custom training loop right here. Let's get down here. We had to actually the way we got the trainable weights was from our VAE model which we had defined. Now given that we have this VAE model right here, the way we access this trainable weights is by using self. So we have self.trainable weights, and then here we have self.trainable weights. And this is simply possible because we are inheriting from a Keras model which already has this different attributes which have been defined. Now that said, let's run this. That should be fine. Training now complete. You could see that we're getting our usual outputs when we making use of the fit method. And then we could go ahead and start with the testing. So we run the cells, and then in here we have some modifications to make. So right here, or previously we had this layers and predict and we took in the inputs and we got some output. Now here we have our model dot predicts. You see that? But this model is a whole VAE model. So since we want to make use of our decoder, we're going to say model.decoder model. There we go. Model.decoder, actually the decoder, because here you define this decoder attribute. So we have model.decoder, there we go, dot predict, and that should be fine. Okay, so let's run this and then see what we get. There we go. You see we have exact same kind of outputs as when we were having our own custom training loop right here. And that's it for the section. Hope you enjoyed it. See you in the next section.